So one of the reasons that we learn about molecular geometry, in other words, the shape of a molecule, and things like polar bonds and dipole moments, is because those factors directly influence the behavior of these molecules. How do they interact with one another? And so the last piece of this puzzle is something called intermolecular forces. And that's what we're going to take a look at now. So the first thing we want to understand is the definition of intermolecular. Intra versus inter. We see both of these in chemistry. Intramolecular forces. Okay, intra means inside the molecules. What we're talking about is a covalent bond, for example. Forces that hold atoms together into molecules. Okay? Intermolecular forces, the prefix inter means between. So intermolecular forces happen between molecules. As you go from solid to liquid to gas, these forces between molecules get a little bit weaker. In solid, remember, the particles are stuck in a position, and so those forces will be very strong. In a liquid, the particles are moving a little bit, and so those forces are a little bit weaker. And then in the gas phase, the particles are very far apart from one another, and usually there's not a whole lot of intermolecular forces at that point. So when a substance changes physical state, like solid to liquid, liquid to gas, we don't break the intramolecular forces. We don't break the forces inside the molecule. The molecule stays together. We break or weaken the intermolecular forces. So in the little diagram up here, you can see the difference between inter and intra. Inter, between, and intra, within, inside. The first of these forces is called dipole-dipole attraction. Now, you just watched a video not too long ago about polar bonds and polar molecules. When we have a molecule that is polar, it has what's called a dipole moment. If you have a bunch of molecules that have dipole moments, those dipole moments can line up to minimize repulsion, pushing away, and maximize attractive forces pulling them near each other. Kind of like magnets. If you throw a whole bunch of magnets together into a pile, they will line themselves up so that the positive end of one magnet is near the negative ends of other magnets, and so on and so forth. Well, these molecules do the same thing. Okay, but these are not as strong as like ionic attractions, where you have a fully positive ion attracted to a fully negative ion, and they attract each other and they stick together really well. Dipole-dipole attractions are weaker than that, and much weaker than covalent bonding. So here you can see these little yellow ovals with a plus side on one end and a minus side. Those are cartoon representations of a polar molecule, dipole moment. Remember, a dipole means that there is one end of the molecule that's getting the electrons that's becoming negatively charged. So if I put a bunch of these together, they're going to try to align themselves in such a way that they maximize their attractions to one another, and that they minimize their repulsion to one another. Remember, like charges repel. That's going to hold these molecules together a little bit more strongly. And if we hold the molecules together more strongly, then it's going to take a little bit more energy to break them apart. In other words, it's going to take more energy to melt them, this substance, or to boil it. Another type of intermolecular force is called hydrogen bonding. The definition of a hydrogen bonding is this. It's an attraction. Again, it's not a full bond. It's an attraction between a slightly positive hydrogen atom and a lone pair of electrons on a more electronegative atom in another molecule, which would be inter, or within the same molecule. Sometimes, if the molecule is big enough, it might hydrogen bond with itself. We're not really going to look too much at that. We are going to look at intermolecular hydrogen bonding. Usually, the hydrogen has to be positive. That means it has to be attached to an element that is pulling its electrons away from it. It's got to be part of a polar bond, and it's got to be attached to a more electronegative atom to become slightly positive. And the thing that this hydrogen is likely to be attracted to is the lone pair of electrons on a nitrogen atom in another molecule, or an oxygen atom, or a fluorine atom. Those are usually the ones we see contributing to hydrogen bonding. Of the intermolecular forces, hydrogen bonding is the strongest. It's nothing more than really a strong type of dipole-dipole interactions, but it's very, very strong. The bond that connects the hydrogen to the rest of the atoms is very, very polar. And so since it's so polar and since hydrogen atoms are so small, the difference in charge between the hydrogen and the other atoms becomes much greater. So the hydrogen gets very, very positive. It's not as fully positively charged as an ion would be, but it's pretty close. And that means it's going to be very, very attracted to a lone pair of electrons somewhere else. Water does this extremely well. So over here we have a water molecule. And you remember from your studies of ionic polar bonds and molecules that the water molecule, each bond, hydrogen to oxygen, is polar. The electrons are moving towards the oxygen, and that means the hydrogens are becoming slightly positive. And the oxygen end of the molecule is slightly negative. Well, those hydrogens are so positive that they really, really want to just be stable. And remember, hydrogen, in order to be stable, it needs a pair of electrons, just two. Well, if you put this water molecule around other water molecules, each water molecule contains an oxygen that has two lone pairs of electrons just sitting there. So the hydrogen is going to be very attracted to those lone pairs, and it's going to form a very strong attraction. It's not a true bond, but it's a strong attraction. These hydrogen bonds in water allow for some very important behavior of the water molecule. Not the least of which is that it's such a small molecule, and yet it has such a high boiling point. Water should boil at a much lower temperature than it does, but because of hydrogen bonding, the water molecules are harder to break apart, and so it takes more energy. The final type of intermolecular forces that we'll look at are called Vander Waals forces. Sometimes they're called London dispersion forces, but Vander Waals forces is the term we'll use. So every molecular compound will have Vander Waals forces, every single one. It's really only important that we consider Vander Waals forces when we're not talking about non-polar molecules, when we're not talking about polar molecules. It's only important that we talk about Vander Waals forces for non-polar molecules. In other words, molecules that don't have dipole-dipole interactions or hydrogen bonding. Because those two are very, very much stronger than Vander Waals forces. So when you have non-polar molecules, the only forces that are going to pull them together are Vander Waals forces. They're very weak and they're very short-lived. The minute the molecules move a little bit away from each other, they break very, very quickly. So they're very, very weak and they don't last a very long time. They're caused by the attraction of one molecule's electrons, which are negatives, to the protons of another molecule, the nucleus of another molecule. So since all molecules have protons in the nuclei of the atoms and electrons, all molecules have Vander Waals forces. But if a molecule is polar, or if it contributes to hydrogen bonding, then Vander Waals forces are so weak that we just ignore them at that point. So we only consider them for nonpolar molecules. This would be a very simple diagram of how it would work. You have a couple of simple atoms, positive charges in the nucleus, negative charges in the electron clouds. When they get close enough to each other, about 5 nanometers or less distance, the protons in the nucleus of one atom are going to be attracted to the electrons of the other atom, and they're going to pull them together. That's what it is. So if you think about it, it sort of creates like an impromptu dipole when they get close to each other. But they're very weak and they break very easily. Okay, so let's take a look at a couple of practice questions. I've got 3 molecules in this first one, HF, HCl, and HBr. Which one of those do you think has the highest boiling point? Stop the video, maybe take a look at the difference in electronegativities, figure out what kind of forces are present, and see if you can answer that question and come back. Got it? So what did you say? Did you say HF? HF is the correct answer. Hydrogen fluoride is the most electronegative bond of the two, the most polar bond, which means it's got the strongest dipole-dipole interactions. And that means it's going to take more energy to separate those molecules from each other than the others. All right, in the second question, we've got a bunch of different compounds here and some intermolecular forces to consider. And I've added ionic bonding to the list because technically ionic bonding is an intermolecular force. It's not really a true bond. It's just an attraction between oppositely charged particles. So, BaSO4, barium sulfate, which of those intermolecular forces is the most important in holding that stuff together? Well, if you thought, hey, barium sulfate is an ionic compound, you're right. Ionic attractions are the most important force holding that one together. How about H2S? Now you may need to draw this, so if you need to, stop the video and draw the structure. See if it's got a dipole moment. See if it can hydrogen bond. What do we think about H2S? Dipole-dipole, that's right. It is weakly polar. It has a very weak polar bond. It can't really hydrogen bond because the sulfur is not one of those elements that hydrogen bonds happen with. How about xenon? Xenon's a noble gas. What do we think? Which of the intermolecular forces is the most important? That's right, London dispersion or Vander Waals forces. Because it's not polar, it's not ionic. Okay. How about C2H6? C2H6 is called ethylene. If you draw it, you'll figure out it's not a polar molecule. It's also Vander Waals or London dispersion forces. P4, that's phosphorus, 4 atoms of phosphorus bonded together in a tetrahedral configuration. London dispersion forces. It's not polar, it's not ionic, no hydrogen bonding there. How about water? Which one of these is the most important for water? Well, water was our perfect example of hydrogen bonding. As a matter of fact, water is one of the best molecules at hydrogen bonding that we know of. And the last one, CSI, not the television show, but cesium iodide. That's an ionic compound, right? So, make sure you've taken good notes. Make sure you really understand what's going on. And if you don't, make sure you ask questions. And we'll see you in class.